So let's say we wanted to know whether education is a good way of predicting whether someone voted for all Canadians, but we only had that sample from last week from that researcher who took a sample of 30 Canadians. Can these data then say anything about the Canadian population in general? So for this, what we need to do is move from descriptive statistics, or describing what the data looks like, to inferential statistics, or trying to say, okay, can this say anything about the population in total, or is it just something about this particular sample that we have? And so this is where we move into hypothesis testing, which is why I highlighted so many times, here's how you create a good hypothesis, because now we're going to be testing our hypothesis. So here's the 5 steps. We're going to go through all 5 steps. 1, we formulate the null and alternative hypotheses. We select a confidence level. We calculate the appropriate inferential statistic. We use a table for the test statistic to find a critical value. And if the calculated statistic equals or exceeds the critical value, then we reject the null hypothesis. And that probably made 0 sense, but we're going to go through it with our example step by step as I try to fend off my computer from a kitty cat who thinks that it's a nice warm place to sit. All right, so let's try this out with our example about voting and education level. All right, so let's start off with stating a hypothesis or a prediction for that relationship between education and voting. So at this point, we are just interested in knowing whether there's a relationship, not the direction of that relationship, because we are treating education as a categorical variable. So at this point in time, we will not know, which causes which, although I think we can probably say that education comes first before voting, that it's not like voting causes people to go get an education. But anyway, at this point in time, let's just form our hypothesis as, is there a relationship or is there not a relationship? So I might say there is a relationship between education and education levels and voting, whether somebody goes to vote. Whether someone goes to vote. There we go. Super specific. There we go. So now we need to state the null hypothesis. So that means the opposite. So the relationship doesn't exist. So there is no relationship between education levels and whether someone goes to vote. Okay, so can we reject this null hypothesis? Can we say that this is not the case, in which case this is the case? All right, so let's figure out how to do this. So step 2, we need to select a confidence level. So essentially, will our sample do a good job of showing us the real, quote unquote, relationship in the entire population? The key question we ask is, and this is a quote, if no relationship exists between the 2 variables in the population from which the sample was drawn, what is the probability that by chance alone we would observe a relationship in the sample data? So that's really, we're trying to figure out if the chance is pretty good or pretty remote that we would observe this relationship just by chance. So to figure out if that chance is pretty good or pretty remote, very scientific terms, we're interested in something called alpha levels. And that's also seen as this fancy little A here. It looks like a little fish. So we express the probability of the relationship we find in our sample that it's just by chance as a percentage. So we are, say, 95% certain that our sample is an accurate representation of the population. We can sometimes also use what we call, say it as a p-value. So we always say p is less than, and then what the percentage is in decimal points. So we'll get this relationship only 5% of the time. And so in decimal points, that's 0.05. So essentially, those are 2 ways that you can say how confident you are. Or not necessarily how confident you are, but what's the chance that you're just going to get it by chance? So essentially, so you would say you're 95% certain, and then all you have to do is essentially 100 minus 95% is 5% that you'll get it by chance. So then you put that as your p-value is less than 0.05. All right, so how do we decide how confident we have to be? So this depends on a whole host of factors. So it includes what field you're in, the size of your sample, the type of hypothesis you're making. So in political science, I'm just going to put out a ballpark general figure. Most studies like to be about 95% confident. In some fields, that's like 99% confident. But note that we are never 100% confident. So that's why we always express it as P, your P value being less than, for example, 0.001, right? Because you know that it's never equal to that. You know, you're never going to be 100% confident, but you want to be at least this amount confident, or this percent confident, because you never really know that a relationship is not just by chance. It still could be by chance. So let's pick a confidence level for our study of education and voting. So just because I normally kind of draw to 95% confident in our field of political science, we're going to say today that we are 95% confident, or if we express this as a p-value, p is less than 0.05. How did I do that? Well, 100 minus 95% confident is 5, and that expressed in decimal points is 0.05. So we want p to be less than, so we want to be at least 95% confident, so we want it to be like at least 95%, so 0.05. Okay. I'll just take this part out though, because that's kind of my thought process. So this would be what our confidence level is. So these things mean the same thing. I'm 95% confident is the same thing as we're, at least saying that, we're okay that 5% of the time this relationship might happen by chance. So that's a good enough level of confidence for us. So if you were doing something like, super like medical research or something, you probably want less than a 5% chance that this is totally random. Like, you probably want things to be pretty darn certain. But for us today, for the size of our sample, all that kind of stuff, 95% confident is A-okay. All right. So now what we need to do is calculate the appropriate inferential statistic. So that's going to depend on what kind of data that we're looking at. Are we looking at a relationship between binary and categorical variables, binary and continuous, categorical and continuous? So here's a quick guide on what to use. So if one variable is this and the other variable is this is what you use essentially. So you can go back to this chart multiple times over the rest of the course, because these are the 3 types of tests that we're going to be looking at over the next 3 weeks. So in our case, we have a binary variable, so did I vote or not, or did the person vote or not, and a categorical variable, so that is the education level. So we are interested in what is known as a chi-squared, not a chi-squared. And it's also written in this fancy little math terms as this like little xy dude squared. Okay, so that's the test we want to do. So we're going to start off by drawing what is called a contingency table. It's also called a cross tabulation or a crosstab. I'll often probably refer to it as a crosstab. And essentially, we want to depict that relationship between education and voting. So let's go back to our data set then, which is right here. There we go. Okay, so we want to go back to our data set. We want to fill out this table here. So how many people who had less than secondary voted? How many who had less than secondary didn't vote? Okay, pretty simple. So let's just go through. One of the easy ways we can do this is, let's just make this a bit larger, is we can sort again, we go to the filter option. So we want to filter, but I already clicked filter. So we want to see the people, let's go by education level, maybe that's easy. So let's just sort. So here are all the people less than secondary education. So of those people, we have 5 that voted, or 5 that didn't vote, sorry. Also, just a hint, right down here, it'll say count and the number. That way you don't have to count every single one. Very, very cool. Okay, so 5 people. So let's go to our less than secondary friends. So 5 of them did not vote. And how many voted? 2 of them. Okay, let's go to our secondary friends. I don't know why they all became our friends, but that's okay. No, didn't vote. We had 3 of them who didn't vote. And we had 7 of them that did vote. Now we go to our post-secondary guys or girls. And we have 11 that did vote and 2 that didn't vote. Okay, I don't know why that's turning out yellow, but that's okay. All right, so now we want to sum it up. So 2 plus 7 plus 11 equals 20. We're going to sum this up too. So 5 plus 3 plus 2 equals 10. So the total number of observations, again, is that 30. And then here we have how many people less than secondary? There were 7. How many people with secondary? There were 10. How many people with post-secondary? There were 13 in our sample. All right. So we filled out our beautiful little contingency table. You could also express this as percentages. So what percentage of the people who voted had each of these? But essentially, this is our beautiful little contingency table. All right, so let's go back to full screen. So now what we want to know is if each of these cells have an important relationship or if they're completely unrelated or independent. So to do this, what we're going to do is we're going to compare the cell numbers with the numbers we'd expect to have if they were completely unrelated. So to do this, we use a very fancy mathematical formula, and we're going to calculate this by hand. Woohoo! Okay, so there's pieces of information we need. So the sum of, that's this big, large E thing going on here. We need the frequencies observed, so that's what we observe. Okay, we got that. And we have the frequencies expected, but we don't have that yet. So we need to do the sum for each of these cells that is highlighted. This formula right here, this part right here, but we don't have the frequencies expected yet. So we're going to have to calculate that by hand. So as I mentioned, we know the observed frequencies, but we don't have the expected frequencies. So to figure out the expected frequencies, we're going to use this fancy dancy little formula here, which involves the total in that cell's row, so it's a TI, the total in that cell's column, so it's TJ, and the grand total. And I like to put this here. Don't be alarmed. We will calculate this once or twice by hand, but the computer will do it moving forward. So don't freak out. I just want you to understand the logic that's going on behind the scenes. Okay, so we need to figure out this expected frequency for each of these cells. Boom, boom, boom. Okay, so that's where we would put them in, but thankfully I already did this for us. So let's just copy this. I just took a picture of, let's move this up here. I just took a picture of it. Okay, let's just make this the right size. There we go. Okay, so what I did is for each of these cells, so this is my observed. I want to figure out what is the expected for each of these cells. So let's start with this one here. So our total of the row is 20. Our total of the column is 7. Our total is 30. And so this is about-ish, for today, let's just round to just one decimal point, is about 4.7. So then I put 4.7 in this cell. So that is this cell's expected value. So then I do the exact same thing for each of these 6 cells, 1, 2, 3, 4, 5, 6. And then I get these expected values. Okay, so now we have each of the expected values, we have each of the observed values. Okay, so now what we can do is we can formulate the chi-squared. So let's go over here. This is where I calculate the chi-square. All right, so we want the sum of, for each cell, the observed minus the expected squared over the expected. So let's go back up here. So for the first cell, what's our observed is 2. So 2 minus, what was our expected? 4.7. 4.7 squared over the expected, which again is 4.7. And that comes out to something around 1.5-ish. You'll notice the squiggly means it's kind of ish, 1.5. Okay. So we do that for each of these cells again. And now what we do is we add them all up for each cell, and we get this lovely number, and that is our chi-squared. So it's about 6.5-ish. All right. So now what we need to do is we need to figure out the next part 4, find the critical value. Okay. So the last number that we need is our degrees of freedom. And again, we use a funky mathematical formula. This time we can probably calculate it ourselves pretty easy. So the number of rows, so how many rows do we have? Let's go back up here. 1, 2. So we have 2 rows and we have 3 columns. So let's do that. So we have 2 minus 1 times 3 minus 1 equals, so that's 2 times 1, 2. So we have 2 degrees of freedom. All right, so we have all the information we need. We know our degrees of freedom is 2. We know that our chi-squared is this 5 or 6.5. So now we can head over to a fancy chart of critical values. So this is just a thing that exists. You can find it on the internet. You can find it at the back of lots of textbooks. And essentially, this is what they all had to do before the computer would find it for them. They would go to the back of their textbook. So what we need to do, we have our confidence interval that we're interested in. So we want to be 95% confident, or P is less than 0.05. We have our degrees of freedom, which is 2. We have our chi-squared, which is 6.5-ish. Okay, so what we're going to do, degrees of freedom, we have 2. Okay, and our p-value we wanted was 0.05, or we wanted to be at least 95% confident. All right. So our critical value then is 5.99. All right, last step now. Our chi-squared, do you remember what that was? It was about 6.5. Does 6.5 meet or exceed that critical value? Is it as big or bigger than that critical value? Well, actually, it's bigger. Woohoo! So our chi-squared does meet or exceed the critical value. So if yes, we can reject the null hypothesis. So it's a yes. So we can reject that null hypothesis. So let's go back up to that null hypothesis that we wrote earlier. Here's our null hypothesis. So we can reject that there is no relationship between education levels and whether somebody votes. So if we are rejecting that, then what can we say? There is a relationship between education levels and whether someone goes to vote. And how confident are we? We are at least 95% confident that this isn't just by chance, which we decided was a good enough level of confidence. Let's say we had said that we wanted to be 99% confident, or so 99% confident would be P is less than 0.01. Okay, so that means we would have had to meet or exceed 9.21, and we did not meet or exceed 9.21. So we're definitely not 99% confident, but we can be 95% confident. And for our purposes today, we decided in advance that that was okay. Oh, and one last thing. The computer does exactly what we did, like super duper simple. And by the computer, I mean, I use a statistics software. Actually, let me just show it to you. This is Stata. This is my statistics software. There's a whole bunch of different statistics softwares that exist in the world. If we were on campus, we would probably spend a class or two playing around with this just so you could get the logic of it. But I'll just show you. So this is the code that I used to get it to tell me the cross tabulation with chi-squared between voting and education. And it would just tell me everything. All I'd have to do is just press a button and it would do all of that for me. But let's go back over here and just talk a little bit about what it shows. So it shows our contingency table, so the number of frequencies in each cell, the row and column totals. It gives us our chi-squared, which again, which is about 6.5, perfect. It's going to be a little bit different on the computer just because they don't round, and we were rounding. And then it gives us our p-value. So p is less than, I don't know why they put equals, because it's always less than, because there could be more decimal points over here, right? P is less than 0.04, so pretty much 0.05, you know, is good. So we can be 95% confident. So this shows us exactly the same thing that we just spent all this time doing. But the key thing is that we did it up here so we could understand what was going on behind the scenes. Otherwise, you just start relying on the computer way too much. Okay, so we've done this. You can go back and maybe grab the worksheet that's blank and try doing it yourself and then checking your work with the video. And then your assignment for this week is to essentially go through all of the 5 steps of hypothesis testing using that data that we used last week, which is right here. So about the countries and the Freedom House scores, development, regions, PEI indexes, voter turnout, all that fun stuff. And essentially what you'll be doing is you'll create a hypothesis. We're interested in the relationship between Freedom House category and a country's region. State the null hypothesis, select what your confidence level is going to be, whether you want that to be 95% confident or 99% confident. So I'm going to just add to express as % confident and p-value, just so you can practice knowing how those two relate to each other. You're going to calculate the appropriate inferential statistic. Hint, we've only covered one, so we're probably going to use that, but explain to me why. You'll draw your contingency table, your crosstab. You'll talk about how many degrees of freedom there are. And then I'm not going to make you actually calculate chi-squared. You can do it by a computer. That would take a long time. And then go through the rest of the steps. And then tell me a little bit about what you think that means substantively, if you do confirm or if you deny the null hypothesis. So that's your activity for this week, your assignment, and it's using the data from last week. So it'll be in the Moodle as of last week. So hopefully that is clear as mud. Again, reach out if you don't understand. I'm happy to go through it again. And then next week we'll move on to another inferential statistic that we can use for when continuous variables or discrete variables start moving into the picture. All right.